Hi, my name is Samantha Melinda, and today I'll be talking to you about proper vertex coloring. I want to go over the outline first. The outline basically just says what we're going to talk about today. We're going to start with an investigation of why this is really important and how it came about. And then we're going to connect that investigation into graph theory. And then we're going to give definitions, do some examples. We're going to talk about planar and then some applications, like real world scenarios of where you would use vertex coloring. That's important because I believe with applications, you can actually see in real life where math takes place. And I think that makes people believe it more. So let's go ahead and move on. So let's talk about this investigation. The most famous graph theory problem is how to color maps. And this is what vertex coloring is. The reason this is important is because in any maps, countries or states, counties, whatever map you're looking at, you might see that every state or such are different colors. Because if these colors were the same right beside each other, it might look very weird because they might look like a giant state. They're a giant state together. You might get confused on borders and things like that, especially if these are maps of other countries, of course. So this question was brought on of like how many colors are needed to color each region on the map so that neighboring regions are colored differently, again, to avoid that confusion. Now, of course, you can color every single state with a different color, a different shade, but that doesn't really match really well. And it's easier to use a handful of colors rather than 50 different colors in the United States case. So let's think about this. This is a map on your right. This is the map in a fictional land of Eulalia. We want to make this map pretty. We want each adjacent region, we want it to be colored differently. So think about that. Think about how you would have a thought process about that. Maybe even try it on your own. See how you can make this a map. Maybe try to color some. But this is what I want you to think about as we go through definitions and how this connects. So you might ask, like, whoa, how is this graph theory? Well, to help you with your investigation, maybe we place a vertex in the center of each region. So it might look like this, where I put a point there, vertex there, and so on and so forth. There's not a right or wrong place to place the vertex, nor is it a right or wrong way to set up a graph, as long as the connections, which we call edges, match. So like I'm going to just do one. This region right here touches this region because of this part, touches this region, touches this region, and touches this region, meaning those need to connect because they cannot be the same color. So the edges here shows connections that cannot be the same color. And that slowly turns into a graph if you do that with every single vertex or every single region. Again, since neighboring regions cannot be colored the same, our graph cannot have vertices colored the same when those are adjacent, meaning they're connected with an edge. So this already lays out a perfect graph to where I know this vertex and this vertex couldn't be the same color. They would have to be different color. Same for this one and this one and this one. We know they have to be different color than the vertex that we started with. So this makes you think it out. This makes the connection more obvious because as, of course, you go through this, the more connections, the quicker or the tougher it gets. All right, so let's talk about some definitions and some words that we would use in this scenario. So given any graph, graph G if you want to call it. A coloring of the vertex is called a vertex coloring. If the vertex coloring has property that adjacent vertices are colored differently than the coloring is proper. Of course, every graph has a proper vertex coloring. It just depends on how many colors you use. You can use infinite amount of colors, but again, like I said, we want to use the smallest number of colors needed to get the proper vertex coloring. And this is called the chromatic number, which is written as xg, which is what we call gamma. All right. And so with examples, let's do some simple examples that do not include anything application-wise. We just want to get the chromatic number. Now, there's a lot of ways that you can attack these examples. I like to just pick a vertex. Typically, it's the vertex with either I go back and forth of either the most connections or the least connections. But what you have to understand that whatever edge connects the two vertices, those vertices cannot have the same color. So something I would look at in the first graph is that one, it looks like every vertex is connected to one another. So I see that this vertex is connected to this one, and so on and so forth. And if you go to any vertex, that is the same. So that should make you ask the question, well, if they're all connected, does any of them share a color? The answer is no. Because they're all connected, they all have to have different colors. And honestly, that is the smallest amount of chromatic numbers that you can find because they're all connected. This might seem like, man, that's a lot of colors, but that's how it goes because no matter what, we did not repeat any. So our chromatic number, we would say, is 6. Now, let's look at one that not every vertex is connected. So you can start at any vertex. Any vertex works. I'm going to start right here. And I'm going to say, okay, well, this one has to be a different color, correct? Okay. The next one is connected to also has to be a different color because it is also connected to the blue and the red vertex. So it needs to be different. Now, this is where you would start duplicating colors as much as you can. So if we look at this next vertex, this one right here, as you see, it's connected to the red dot and the green dot and 2 other black dots that we have not given a color yet. So because it's connected to the red and the green, but it's not connected to the blue, so I can actually duplicate the blue, which is nice because that makes sure that I'm getting the lowest number possible. So let's look at the vertex to our left. It's connected to the red and the blue, but not connected to the green. So I can duplicate the green. And the last vertex is connected to the green and the blue, but not to the red. So we're going to duplicate the red. And this represents a chromatic number of 3 because there's 3 different colors. All right, so let's do the last one. Now, again, you can start wherever you want. I'm going to start with the most connections. So I have the red. My next connection would be blue. That's just one of the connections I chose. The next connection, now the next connection is this vertex right here. The reason I'm already outlining in blue is because it's not connected anywhere to the other blue vertex. So I'm going to make that blue. And the next connection to the right, I'm also going to make it blue because it's not connected to any other blue vertices. So if we connect this all, the top vertex is connected to all the blue vertices, but it's not connected to the red, so we can go ahead and color that red, making our chromatic number 2. So there's some examples of a very high chromatic number and a very low chromatic number, and 2 is, of course, our lowest chromatic number that we can get. All right, so let's talk about planar, and we're not going to spend too much time on this because coloring is more significant. But if you convert a map or a graph, the edges between the vertices correspond to borders between the countries, like we talked about. And this is a good idea to have as you think about the investigation. You should be able to connect vertices in such a way where the edges do not cross. These graphs represent maps, which we are all planar. So meaning that if the edges do not cross, no matter how many ways you write them, it is a planar graph. The largest chromatic number of any planar graph, we like to say it has the 4-color theorem. So if G is a planar graph, then the chromatic number of G is less than or equal to 4. Thus, any map can properly be colored with 4 or fewer colors. So if it's planar, it has 4 or less colors. If it's not planar, it could have infinite amount. So that is an introduction to planar. So let's actually go back to our investigation. So I have already created this graph that we started in the previous slide. So let's go ahead and try to color it just like the examples we did above. So I'm going to start with A. And so it is connected to B, C, G, and F. And again, you can label these any way you want. You can make up fun names or anything like that. So let's go ahead. B would have to be a different color than A because that's who it's connected to. C would also have to be a different color of A and B because it's connected to both. So I'm going to make that purple. Or actually, let's make it blue or red. All right, the next one, G, is connected to A and C. So it needs to be a different color. But it's not connected to blue, so that is why I'm duplicating blue, because I want to duplicate as much as I can until you're stuck where you can't. F is connected to green and blue, so we're going to make that red. And then you can really go anywhere else from here. I might go to I just because it has a couple more connections that have colors. So I is connected to red and blue. So I'm going to make it green because it's not connected to green. G and I would be connect with H to make it red. M, you see, has a connection of red and blue, but no green. So let's duplicate that. J would probably have to be blue because look, it has a connection of from I, H, and M, which is red and green. So let's make that blue. And you might realize around J, you would just kind of go back and forth between red and green. Except with D. If you look at D, it is connected to a blue dot, which is B and J, connected to a red dot, which is C and E, and a green dot, which is I. And so D is going to have to be a totally different color, which I'm going to make purple. So this makes the chromatic number 4. And so when we color this map, we would have to color in 4 different colors. All right, so let's look at an application. So this was, of course, the investigation we started with, and this is how you would color a map if you were given a United States map and all the 50 states. All right, so here's an application. The math department plans to offer 10 classes next semester. Some classes cannot run at the same time per like teachers or times or something like that. How many different time slots are needed to teach these classes? So you have classes A through J, which are the vertices you see here, and your conflicts. These conflicts are depicted by the edges. So, such as A has a conflict with D and I. So, as you see, there's an edge between those two vertices because we cannot have them at the same time slot. So, coloring makes that more aware. Like, oh, A, I, and D have to have different time slots. And of course, we can repeat time slots if they have no conflict. So, B does not have a conflict with A. So you could actually have A and B at the same time. So that's what you have to look at with applications. So let's start with, again, you can start with any vertex you want. I'm going to start with A because, hey, I talked about it. So A is connected to I and D. So let's make I red. And I is actually never connected to D itself. So let's make D red also because we want to duplicate. Then I might go to B. B is connected to both I and D, which are red. So I'm going to make B blue because not connected to A. So we're going to duplicate. Another one I might do is J. J is connected to B, which is blue. And so I'm going to make J red. The next one I might see that has two connections is H. It has I and J. So let's go ahead and make that blue. And then let's look at E. Oh, E's our different one. E is connected to H and I, which are blue and red, and we don't have any other colors to duplicate. So E is going to have to be its own color. C is connected to a red and a green, but not connected to a blue. So let's make that a blue. F is connected to a blue and a red vertex, but not connected to a green. So that was a good thing. We created a second or third color. And then G is only connected to red. So it could be blue or green, but the chromatic number still stays the same. So it's okay to have different colorings, but as long as your chromatic number is the same, that is okay. So the chromatic number is 3. So it's okay if your coloring does not look the same as mine, as long as your chromatic number is the same. All right, here's another application. A radio station broadcasts their signal at certain frequencies. However, there are a limited number of frequencies to choose from. So nationwide, many stations use the same frequencies. This works because the stations are far apart and their signals will not interfere. So suppose we have 10 new radio stations and are set up in a certain unpopulated region. The radio stations are set up in a certain unpopulated region and are close enough to each other to cause interference. So here are the interferences that you might see. They are depicted by X. I am going to add an X here because there should be an interference there. And then I created that graph through those interferences. Now I labeled them A, B through J. As you see at the end of these names, there's different letters. So that's how I named the vertices. And then again, your connection errors are depicted by the X. And these are edges that you want to create. So I want to make a connection between A and C because we don't want the same radio tower because they could have a conflict. So I want you to go ahead and color these on your own, so pause the video if you want to try it on your own, but the coloring should end up being A. Let's make A green. That makes C blue, J red. This one's a little bit a heavier color, purple, orange. Ooh, this one could duplicate, which is good. This one also can duplicate. Same with this one. And there's a good amount of duplications, but unfortunately, this one is a higher chromatic number, which is okay. So the chromatic number here, and hopefully you did this on your own, is 5. So there are 5 frequencies the station can use. So this is a good practice. Please go back and use this practice. And here's the resources I used. Thank you so much for tuning in, and I hope this helped you learn about vertex coloring.